Welcome you all to Module 3, Interfaces in System Verilog. We'll be discussing some exercise problems here. I'm just taking a small example of full adder here, and I'll be showing how interfaces can be used in a system Verilog. As I told you all, the syntax for interfaces, interface and end interface, that's what is been shown here. And in between this syntax, we can include different components which needs to be bundled inside interface. And also we can include a task or function in it. Right. So for a full adder, we all know that it has three inputs, A, B, C, N, and two outputs, sum and carry out. So C out is the nomenclature given here in this example. So we have all these five components which have been declared as logic, and they are bundled inside the interface. The name of the interface is full underscore adder underscore if. Right. So other than the components being bundled, we also have added a function which does the evaluation of sum and cout. So the name of the function is add, and it's automatic. So you know the concept of a function with automatic and without automatic. So by default, they are static in nature. So we have understood all those topics related to function and task in our earlier presentations. So inside the function, I have declared sum as A XOR B XOR Cin and cout as AB or ACin or BCin end function. So this is the evaluation which is being done by the add function. We next have to define our DUT. This is the DUT, that is design under test, which is starts with the keyword module and module name. The module name is full underscore adder. And now instead of passing the different inputs and outputs of full adder, we use interface, which is nothing but the bundle representing all these components. So we just pass full underscore adder underscore if with the instance name of this interface as if1 inside the DUT, right? So that is an argument which is being passed. And then I'm using behavioral modeling. So always underscore com. So this always block will get triggered whenever the combinational variables A, B, C, and get triggered, right? The values change. This gets the statements inside always gets evaluated only when the variables A, B, C, and gets triggered. So always underscore com inside this block, I'm calling if1 dot add. Now what is this? If1 is nothing but interface name. So interface name if1, which is calling dot add. So add is nothing but a function inside interface. So this in turn will call this function, right? And evaluation of sum and cout happens here. So this is how DUT is written. Okay, so DUT is getting linked to the interface. Now, in order to give test cases to this DUT, we are writing a test bench. The name of the test bench is module test. Test is the name of the test bench. And inside that, we are calling the interface, which is full underscore adder underscore if one, that's the instance of one instance of the interface. And we are calling one instance of DUT, which is F9. And we are passing the parameter if1. This is the interface which is being passed as an argument to our DUT, right? So this is nothing but the signature of the DUT inside the test bench. So this is the signature which I'm matching, okay? Then inside the test initial begin, I'm giving test cases. Now in this example, $display command displays whatever is within the double quotes here on the screen. And what are the different test cases? We are generating 8 different test cases here, 8 test cases using for loop. I'm just saying if1 dot a comma if1 dot b comma if1 dot cin equal to I. This happens for 8 times. So initially I will be 0. So 0, 0, 0 will be assigned to A, B, and Cin, which are bundled inside the interface. Next it is 0, 0, 1. Next is 0, 1, 0, like that up to 1, 1, 1. So these are the different test cases which will be given to the inputs of the full adder. And the DUT then invokes this function, which in turn will evaluate this expression of sum and cout for 8 different test cases. It evaluates the value of sum and cout, and that gets displayed using $display command. Okay, so this is how interface is used in our DUT. And then a test bench is written, which will invoke the DUT connected, which is connected to the interface in turn. Okay, and this is a example of not only the components being bundled in the interface, but also we have written in function which evaluates our sum and cout. Okay, so next example, as we see that we can also use task inside the interface, but tasks generally are will have fault, will may not behave well because they cannot do proper synchronization with the DUT and test bench, and hence instead of task we can also use mod port. Which is used to declare which is used to define the directions of the signals which are used in the DUT. So ABC in of the DUT are input, so that you can define in the mod port, and sum and cout are actually the outputs of the DUT. So that is again defined in the mod port here. So this is bundled in the interface now. Now, what is the thing to be done is, so I'm not using function here, but I'm using mod port. That's all. So the evaluation of sum and cout will hence be done inside the DUT. So earlier function used to do the evaluation, but now since I've not defined a function or a task here, I'm using mod port only to mention the directions of the input and output, a direction of the signals. So evaluation of the sum and cout is done inside the DUT, which is inside the always block, right? So that's the only difference. So you can either use function, which does this task for you, or you can use mod port, mention the directions of the signals, and use them inside the DUT to evaluate your equations for sum and cout. So even that can be done. The rest all thing is same as we did in our earlier example. Okay. The only difference is we are having mod port here, which will tell me the directions of the signals, and I have inside the always actual expressions, which does the evaluation of sum and cout based on the directions mentioned by the mod port. So they link with each other. So this is the other way of writing in full adder using interfaces. So same way we have written, I'm showing you an example of 2 to 1 mux here, wherein a 2 to 1 mux will have A, B as the input, and cell, I'm taking cell as the select line, and Y as the output. This is my 2 to 1 mux. So I need to bundle this in the interface. So I'll say logic A comma B comma cell. These are all the inputs, and logic Y, which is the output. Then I want a function which evaluates my 2 to 1 mux. So function select, return type of the function is mandatory. So return type is logic here. So it returns based on the value of cell, based on cell being 0 or 1. If it is 0, it selects A to Y, and if it is 1, it selects B to Y. So based on that, a return is done, end function and interface. So inside the DUT, this is my DUT. So inside DUT, inside always underscore com. Now, because if I just put always, then it becomes an infinite loop. So I want this always to act only when the input variables trigger. So combinational variables of mux here are A, B cell. So only when A, B or cell get triggered, this has to get evaluated. So I don't want an infinite loop. I want it to act only when the input variables get triggered. That's the reason I put underscore com here. So when I say if one dot y is equal to if one dot select, then this function will be called, which is in the interface. That's the reason I put if one dot select. So this function will be called, and based on the value of cell, A or B will be written, which gets stored in Y. So this is what happens when I have a 2 to 1 mux using interface, which also has not only signals, but also function bundled in it. Now, in order to invoke this DUT and the interface, we have to write a test bench. So the name of the test bench, which I've mentioned here, is test underscore mux. So I'll be invoking the interface as well as the DUT. So this is my interface, which is a function-based interface. And this is my DUT, right? So what are the different test cases I'm giving? I'm giving 8 different test cases here. So this is with the for loop, and then A, B cell, which are bundled in interface, are assigned value of I, which is 2 down to 0. That means MSB gets assigned to A and LSB gets assigned to cell. That is what I'm doing in this example. Okay. So I of 0 gets assigned to cell. I of 2 gets assigned to A. That means I of 1 will automatically gets assigned to B. So for the first time, I will be 0, 0, 0. So A, B, C, A, B and cell respectively get 0, 0, 0. Then it will be 0, 0, 1, like that up to 1, 1, 1. They get assigned to AB cell based on the for loop value I. Then we give a pause of or a time delay of 1 every time here. This is just to bring in synchronization between DUT and test bench. So hash 1 is hash 1 or any time delay you can give here. And every after every one delay, I'm displaying the value of A, B cell and Y. So Y is the value which is the value which written from the function sends back, right, to the DUT. So that's the value which gets displayed. So that's about how you can use interface along with the function for a 2-to-1 mux. The same way, if you don't want function, then you can replace with mod port, which I'm showing here. So I'm just replacing the function with mod port. The name of the mod port is DUT. You can give any name here. And then I'm mentioning the directions of the signals of my DUT. So AB cell is the input and Y is the output. So I'm just mentioning the directions here. While actual evaluation of my DUT, what all expressions I need for my signals. So that is being put here. Instead of calling the function, what I'm doing is I'm evaluating them actually, or actual equations are being put inside the always block here. So that is what I'm doing. So here it was written in the function, the evaluation was written in the function and the function was being called inside the DUT. But here in the DUT, we are actually writing the expressions which function would have done otherwise. So that is what we are doing here. And all other things are same. The test bench is same. The only thing is the mod port, and then because it's mod port, how to define the other equations inside the DUT. That has to be mentioned properly. So this is about how interface can be used to define a bundle of signals of a particular design under test. So that's two examples. And now coming to cover groups, I would like to show you an example for cover group here. So that is, let me just show you all an example which has been written for a particular combinational circuit, which I'll be showing here. Let me just open that program for you all. So the cover group is written here for 2-to-1 mux. See how we have mentioned the module. This is the DUT. The DUT name is again mux 2 to 1. This is the name which has been given here. So the directions, because it's a DUT, I can give directions to my inputs and outputs, direction to my signals. So in 0, in 1 and cell are my inputs. So that's the reason I've given input to their input direction to the signals, and out is the output signals, so output logic out. Then I'm just evaluating this expression in the DUT using a data flow style, which is also called as continuous assignment style. So I'm just saying assign out is cell question mark in 1 colon in 0, indicating that if cell is 0, it gets in 1, else it gets, if cell is 1, it gets in 1, else it gets in 0, which gets assigned to out. So that is what we have written in the DUT. Now, in the coverage, see, I need to define cover group now in order to do functional coverage of my 2-to-1 mux. So what is the what is the syntax for that? I have to include cover group and then cross. These are the components which I need to include, and that should be inside a class. So what is the class name I've taken? Class mux underscore coverage. That is what the class I've taken. And you have to mention inside the class all the cover group variables which are using in the cover group. So it's in zero in one cell. So it's of type logic. So logic is being defined here. And what is the name of the cover group I'm taking? It's CG underscore mux. So syntax for cover group is cover group followed by cover group name. So it's CG underscore mux, which is being taken here. Then you have to define the bins for your cover group based on what are the variables you are monitoring in your cover group. So the bins are one I'm taking for cell. So you have to declare it as cover point cell. You have to name it actually with a label. So cell underscore cover CP is the label I'm giving it as, and cover point cell is the syntax which you need to mention. So cover point is the syntax followed with the variable name, which is cell. So cell is a one bit variable. So two bins I've created, one bin for 0 and another bin for 1. So I've named it as bins S0, bins S1. And the value being monitored is 0 for S0 and 1 for S1. Then I have one more variable under cover point, which is in 0 and in 1. Two variables, I'm merging them, concatenating them here. You can take them individual like you did for cell, or you can combine them. So I'm just showing you the ways in which you can do it. So in 0, in 1, I've concatenated and prefixed it with cover point. The label for this I'm giving as inputs underscore CP. You can give this label anything, but it should always be relevant to the variable you're working with. So then I'm creating 4 bins here. The reason is I have 2 inputs, so I'll be having combinations of 2 raised to 2, which is 4 different combinations I can have with 2 inputs. So I'm creating 4 bins here, which is a bin, one bin for 0, 0, another for 0, 1, then 1, 0, followed with 1, 1. So 4 bins. And then I have to just say cross coverage, which is the syntax for that is cross. Okay, so cross followed with what are the variables you're monitoring, which are in your cover point. You have to mention them. So cross followed with cell underscore CP and then input underscore CP. You have to mention the labels right here. Okay, so cell underscore input underscore cross is a label for that. Okay, so you have to remember these syntaxes whenever you're defining a cover group. Okay, so cross is the syntax followed with the labels of cover group I'm mentioning here. And the label of cross is cell underscore inputs underscore cross, which can be anything. I've just named it according to my convenience. Then once you do this, you have to terminate the syntax to terminate coverage is cover group is end group. So cover group started here and I'm ending it here. So this is inside the class mux underscore coverage, right? So DUT is separate. I've written outside this class, but inside the class mux underscore coverage, I've defined the cover group based on how many bins I want for each variable with following the syntax. Then I've terminated with end group. Then I'll start a constructor for my class. So function new, and inside the function new, I'm allocating memory for my cover group. What is the syntax to allocate memory for my cover group? I have to just call the cover group, then say equal to new. So that allocates memory, right? So I'm using a function new and allocating memory for cover group, then end function. That's the way you have to do. Then followed with, I'm writing a task here, which is a task sample. And here I'll be giving all the test cases for my cover group inputs. So what are my cover group variables I've taken? I've taken two in I0 and I1 as one of the cover point and cell as another cover point. So include everything here. So logic 1, logic I0, logic I1, logic S. Then you give values to these. So in 0 is I0, in 1 is I1, and cell is S. So this is being passed from the test bench. Okay. So to the task sample. So then you are assigning whatever values are being passed from the test bench, you're assigning it to in 0, in 1, and cell here. And then CG underscore mux dot sample. What it does is it monitors the changes in the cover group variables. It monitors it and it will see how much is covered by the how many test cases are being implemented and what is the coverage which has been applied to the DUT. Okay, so end task, and then once you do that end task and end class, you're done with the class mux underscore coverage. So what all we have defined under in class mux underscore coverage, we have defined the cover group, which mentions the bins of each variable. And then we have defined a task, which is always task sample. So what will sample do? Task sample will assign the values which the test bench passes to the cover point variables, to the cover point variables which we have assigned here, okay, which we have declared here. Then coming to the test bench now. In the test bench, I'm invoking, I'm declaring these variables of the mux with I naught, I zero, I in zero, in one, cell out, which are logic type. And then initially clock is zero. Why I need a clock here is in order to sync the you can also use delay here in order to sync DUT and test bench, but I'm using a clock to bring synchronization between DUT and test bench. So I'm declaring a clock equal to 0. Then I'll instantiate my DUT, which I've written here. So this DUT is nothing but it's having only the functional behavior of my mux 2 to 1, which I've written here, right? I'm using a data flow style. So I'll be invoking that DUT, and then I'll be also invoking an instance of mux underscore coverage, which has my cover group and the task here. So mux underscore coverage, COV, is an instance which will call new function which allocates memory to the cover group. Then I'm toggling the clock, which for every 5 time scale, the clock gets toggled. And in the loop, in the initial begin, I'm giving test cases to my cover group. Okay. So what happens here? Before I start giving test cases, I'm waiting for a period of 2 clock periods. That's the reason I'm saying repeat of 2 at posage clock. So 2 clock periods, it does nothing. It just waits. And after 2 clock periods, I'm giving 8 different combinations of inputs to my mux, 2 to 1 mux, for in 0, in 1, and cell. So 8 different combinations using for loop. So these are the test cases. And then I'm invoking the task cov.sample. I'm invoking the task, which is this, right? So when I say cov.sample, this sample invokes this task, right? And this happens for every one sample is being given, and the cov.sample is invoked, the task is invoked, and it waits for 1 clock period. This is just to bring no overlapping, we have to avoid overlapping between DUT and test bench. So it has to happen one after the other, so in sync. That's the reason I'm giving a delay. At passage clock gives the delay. You can also give #1, #2 if you don't want the delay in the form of a clock. You can do even that, right? So every test case is given and it's monitored, and there is a pause every time for the next test case. So that is how this works for 8 times, and the coverage is monitored during that time with the sample task, right? And then we put the coverage. We display the coverage using the function get underscore coverage, right? That's the built-in function. So you just need to call cov.cg underscore mux dot get underscore coverage. That's the syntax, because our coverage is CG underscore mux, right? So that's the name of the cover group. So, and what's the instance? We have COV as the instance. So COV dot, then cover group name dot built-in function get underscore coverage. That will tell you how much of the functional coverage has been done in this code, right? But see, I have 3 inputs basically for a mux in this 2 to 1 mux. So 2 inputs and 1 select line. So 3 inputs basically. So what are the different input combinations I can have for this mux? 2 raised to 3, which is 8. Now, since all the test cases have been checked here, all the 8, my coverage will be 100%. So when you run this code on EDA Playground or Vivado and check the answer for this last statement, it should be 100% as the answer, telling that it has covered all the values, all the test cases have been covered for this function. That is what it has to convey with the answer of 100%. Okay, so this is about interface programs and a cover group program. So this is how you're supposed to write cover groups for your program. That's the functional coverage test if you want to do. This is how you have to write and understand how coverages, functional coverages happen in System Verilog. Thank you very much.